All right, 1.6, we're going to talk about the topic of parent functions. And to a certain extent, the big picture on them is a little bit incomplete till we get through section 7, because it kind of goes like this. A parent function is what we use to kind of split up functions into what we have called families. Okay? Different kinds of functions that display totally different behavior and are used in different situations as a result. Parent functions are the ones that we haven't done anything to them. Okay, in section 7 we talk about transformations, where now we start to do stuff to the equation. Typically 3 things that we'll look closely at: that we shift functions, we stretch them, and we reflect them. Okay? But this is before we do any of that. So it's almost like we're outlining most of the functions that we'll deal with. Okay? Shouldn't be any surprise at all where we start. Okay? What a lot of you probably recognize as our 2 favorite functions. Okay? Lines. The parent function for a line would be y equals x. Okay, really, really basic. It's got a y-intercept of 0 and a slope of 1. I'm just putting in all these points. I don't need to make a table for this one. Some of the others you might. Now, if we think of y equals mx plus b, this is 1 times x plus 0. And the way we look at lines is if we start to change those numbers to anything other than 0 and 1, we're starting to take this parent function and we're transforming it. Okay, we could shift it. If we throw in a negative value for m, we could reflect it. And we can stretch it by changing the slope as well. The shift would come with changing the y-intercept. But if those numbers are anything other than 1 and 0, you're talking about some transformation of this parent function. With quadratics, y equals x squared. Okay, it's the one that was on the top of this page on the previous slide. We saw a parent function for a quadratic. Nothing super crazy going on here. If I wanted to put together just a quick little table, I could put in -2 and get 4, put in -1 and get 1, 0, 1, and 4. And would look roughly something like this. Okay? What's going on here, if we were to write this out the long way, we have y equals 1x squared plus 0x plus 0. Okay, there's these other values for a, b, and c. This is where I'm kind of getting ahead of ourselves and looking at section 7 when we start to do transformations. But that's like your most basic quadratic. And you can see it looks very different from a line. It's a curve. It changes direction. In fact, it changes direction, exactly 1 time. Used in very different situations from a line, right? That's kind of what we're doing is we're kind of outlining our parent functions to say, here's kind of the different types of functions that we have. Each is used for a different situation, depending on what your data is about and what kind of growth or decay or rate of increase or decrease that you're dealing with. Okay? And this isn't going to be an all-encompassing list. There'll be a few more that we get to later on that we don't have today, but this is kind of most of them. Okay? So quadratics, there's a lot of things we could do. Again, we can shift it up and down, side to side. We could reflect it. We could stretch it to make it wider or skinnier, but this is kind of like the starting point. A few other cases to take a peek at here. Here's a cubic. F of x equals x cubed. here is one we don't use a ton, but it's worth mentioning, the square root function. And this last one here is 1 over x, or what we call a rational function. Okay? Now, if you wanted to pause at this point in time, you certainly could. I'm going to start to put together some table of values and give you some good x values to use here. The square root's a little bit funky. Using numbers that are perfect squares, like 1, 4, and 9, are going to be helpful. This one, if you do pause at this point, I wouldn't do this one until we can talk about it. I'm just not super confident at this point in time with how much you saw rational functions from last year that you'd have a super good idea of what that graph looks like. Here's the rest of the table for the cubics, though. Goes through 0, 0. Notice we had 1, 1, negative 1, negative 1. And then it went up to 8. And down to negative 8. And we get kind of this interesting looking curve here. I kind of missed the point there, but I'm not that concerned about the points as much as I am the shape. Cubics increase faster than quadratics. They don't have that parabola shape. We use them a decent amount. They work really well for geometry problems that involve volume. You know, length, width, and height, 3 dimensions, third power. They work great. Okay, but that's for the most part what they look like. And again, what we're after right now is we're not doing anything to it. That's the one that we would start with if we wanted to do a transformation. It's a cubic. It's kind of like you should know it when you see it. This one starts at 0, 0, goes through 1, 1, 4, 2, 5, 6, 7, 8, 9, 3, and kind of looks like that. Now, some of you might have one that's down there too that would actually fail a vertical line test. Okay, a couple different ways you can go with this, because if you drew it like that, you're not wrong. You're actually correct. If you took the square root of 4, you could have plus 2 or minus 2. This isn't a function because you put in an x value and you get 2 answers. If we're thinking about the square root function, a lot of times we disregard those negatives, not because they're not actually there, but because if we're looking at a square root model that actually has an application or a context, we're rarely interested in those negative answers because they have no practical meaning in the problem. Okay, with those numbers in there, you can see it's a quadratic that kind of looks like it's been tipped over on its side. But we usually just look at the top half, which kind of starts to increase quickly and then starts to slow down a little bit as x gets bigger. Here we'd have negative 1/4, negative 1/2. You'd get an undefined value if you put in 0, and then 1/2, and 1/4. Okay? You get something that looks like this. Again, I'm not paying super close attention to the points because that's not really what I'm after right now. I'm going to mark here x can't be 0 because we saw that when I put in 0 I didn't get an answer. Rational functions look something like that, and again right now that's what I'm after. That you see that type of graph that your mind goes to. This is like 2 functions that are being divided by each other. Okay, it's a little bit more specific than that, but that's a great place to start in terms of considering rational graphs. The really big characteristic is that vertical line that we saw at x equals 0, where there is no graph because we put in a number and didn't get an answer. In application problems, you'll see we're typically more concerned with this curve than the one down on the bottom left, just because the context of the problem usually gives more meaning to that part of the graph. But those are 3 good ones to know because we'll work with these a decent amount. Again, there's really, looking ahead, there's 2 others that we're really going to look at pretty closely. They kind of have their own separate chapter because I want to highlight these because for the rest of Chapter 1 and Chapter 2, these are the ones that we're just going to dive right into and we're going to work with a lot. The other 2 that are out there are exponential functions and logarithmic. They totally go together because they have a very particular relationship that we'll look at closely. That's Chapter 3, but because it's just going to be a while, you know, we'll leave those be for a bit. Last topic for today, the good old piecewise function. Okay, we actually saw one of these in an application problem in, I don't know, I don't remember the section. It was a couple sections ago. It was one on alternate fueled cars. I think it might have been section 3. That data that we had in the alternate fueled cars problem, really when you got down to it was curved, but we didn't really want to use a curved equation to model it. Those tend to get more complicated, so we did it with 2 lines. And I think the years were like 1995 to 2000, something like that, that we could use 1 line. But then when we got to the year 2000, we had to switch, and we had to go use this other one because the slope changed dramatically. We can do that. Okay? You just have to use what's called a piecewise function, where you're saying, I've got multiple functions. You just need to know which one to use and when. Okay? So here, again, I'm sticking with lines, and I've got these 2. Because the first one says if x is less than, it's probably worth making sure we're clear on that. Less than or equal to 1, use that 1 on the top. But as soon as we start talking about x values that are greater than 1, we have to switch, and now we're going to use this other line. Okay? Well, I'm going to start graphing the first one. It's got a y-intercept right here. I go up 3 over 1, down 3 over, whoops. I got my numbers mixed up here. Not mixed up, just, well, mixed up, but backwards. The y-intercept should be 3, and then it should be up 2 over 1. And I'm drawing in my line here, connecting my points. And notice how I stopped right there. I'm going to put an arrow down there because those x values can keep going negative. But notice this point right here, which is 1, 5. I stopped. Okay, and I'm not putting an arrow because this graph doesn't keep going. Because once x hits 1, I'm supposed to stop using it. Okay. Now I'm going to include this point, so I'm going to put a nice filled in circle. Okay. But once I get past it, I need to switch over, and now I'm using this one. Okay. Now I plug in 1 into this one. If I plug in 1, I get 3. So that's going to be a point at 1, 3, but you have to remember that's like the cutoff point, but 1 went with the 2x plus 3. So it's kind of like I need to mark that this is the place to start, but I don't want to include this point. So notice I put an open circle. Okay, that's where I'm going to start, but when x is 1, still go off of 1, 5. As soon as I get past it, like these points here, now that I use the slope of -1, then I'm going to use this particular model. And it can go as far as it wants past x equals 1. And that can keep going on forever. Okay, so you got to be a little bit picky with how you do your graph to make sure it's really clear that at x equals 1, I'm using this one right here. Okay, but as soon as I get past, then I jump down and I use that second one.